Welcome to lecture number 34. In the last 3 to 4 lectures, we have focused on the length scale issues in materials engineering. So, now we are going to change the topic. We will be talking about some of the advanced deep learning methods. Here I will focus on basically few techniques which are relevant for materials engineering. But before that, let me tell you that for the section on the length scales, different length scale issues in materials engineering, I hope you have got a good glimpse about the whole thing, in the sense that it is a vast topics. So, we wanted to provide you some basic knowledge on this topic. Idea of providing that section was mainly related to make you believe that we can generate a lot of data using simulations or using theoretical calculations or computational techniques, like whether it is a computational technique like KANPUR or phase field modeling or DFT or MD simulations. So, that each of these techniques can provide you a lot of data which are reliable and can be used for application in machine learning and deep learning. That is why we wanted to teach you that. But if you want to know details of each of these techniques, you need to follow different courses in NPTEL as well as books and the papers. And these are actually part of the whole subject called computational material science, and which is taught in various universities and institutes. So, let us move on. So, we will talk about advanced deep learning methods in this lecture, but as usual first we will look into some of the recaps what we have learned so far in materials design and different length scale. These recaps actually are going to provide you one important aspect, that is the snippets of the discussion which are important for you to learn and move ahead. So, you know, we can use advanced computational tools, computational material science tools to do various kinds of calculations. We can actually use them to reduce the cost and the time consuming experiments. It is widely been used for alloy design or other material design. So, first we can do first principle calculations like DFT, density functional theory, or MD or molecular dynamics, to find out crystal structures, stability of them. Not even that, we can even find out electronic contributions or electrons, role of electrons, distributions, everything using first principle calculations. This is also sometimes known as ab initio . So, this is what is being taught by the guest lecturer Professor Tarun Kumar Kundu for the last 2 lectures, lectures number 33, 22 and 33. Then from this information we can actually calculate lot of thermodynamical parameters like enthalpy of mixing, entropy of mixings, or we can actually determine experimentally also, extrapolate also, I have shown you in my lecture, and find out phase equilibria, phase diagram informations. It can allow us to find information of phase equilibria of the equilibrium phases as well as non-equilibrium or metastable phases. So, that provides us the phases present, but it does not provide you microstructure. And as you have been told that microstructure is the connecting link between the processing and the properties. So, how to get it that? So, for doing microstructure we have discussed about phase field, right. Phase field is a technique which is widely used to generate microstructures or understand microstructures, and phase field requires you to requires the important aspect like interfacial energies or state energies as well as mobilities, the diffusion coefficients of this. So, here we are showing a microstructure in which precipitates are present in a matrix like aluminum copper alloys, where precipitates are basically present in the aluminum matrix. Now, these precipitates can be formed by aging treatments. So, we can actually understand that also. Finally, our basic goal is to connect the microstructure of the properties such as mechanical functional properties. So, therefore, we also need to understand micromechanical models for that, but remember we are not going to discuss about this in this course. Okay. There are many micromechanical models which can be used to predict even mechanical properties. So, hence our discussion is limited to them. So, And many times if you want to get a full scale microstructure, these slides I have shown you already, we need to connect thermodynamics and kinetic databases. Thermodynamics provides you phase stabilities, kinetics provides you information about these phase transformations, how the phases are going to form, that can be obtained from that. So, basically experimental diffusivity data or diffusivity data from atomistic calculations like MD simulations can be used to find out mobility databases. And in fact, one can also use machine learning tool to optimize that data, and that is what is used in DICTA or diffusion interface control phase transformations, transformations, diffusion and interface control transformation, that is called DICTA. Diffusion is D, interface is I, control is C, and transformation is TRA. So, we can use thermocal using FANDAT or even thermocal database also, and find out phase diagram information is shown here. We can also find using diffusivities, we can find out the rate of reactions of phase transformations. And once you have the microstructure using for phase field simulations, we can find out elastic properties. Interfacial properties has to be used to generate the microstructures, that is the interfacial energy, strain energies, all these aspects that also can be calculated from ab initio simulations. So, why thermodynamics? Because properties are what is important for us. We want to design materials with target set of properties, mechanical, chemical, electrical, magnetic or thermal or any other properties, and properties are dependent on structure, as you understand. Structure means atomic, crystal, grain structure, phase distribution, defect structure. So, in a nutshell, from atomic scale to the micron scale, and then you make any component by processing, and during processing you are using different kinds of variables like temperature, pressure, stress, strain, and chemical composition of the alloy, right. So, that is how is the whole processing structure property relations, and thermodynamics is the basis for understanding this, because the material can respond in terms of the change in temperature, change in pressure or even compositions, and we can understand that. And finally, we are interested to know the performance, and which is dictated by connecting these three links together, processing, structure and properties. So, that is the thermodynamics plays the most important role, and in thermodynamics we have to use data mostly to calculate the phase diagrams and phase equilibrium informations. Data can obtain from experiments as well as fast principle calculation, and then we can actually predict different kind of phases. Nonetheless, we can use statistical thermodynamics also to obtain some of the thermodynamics data. So, what are the different properties we are looking at? We are looking at enthalpy, entropy, Gibbs free energy, or thermal expansion or the heat capacity as a thermodynamic properties. We can also look at kinetic properties like diffusion coefficients or shear viscosities, right. On the other hand, mechanical property like elastic and plastic properties, as well as the interfacial energy properties like all these things, stacking polar energies, twin dislocations can also be calculated using fast field simulation, fast principle simulations, and this can be all used to gather information about the phase transformation, phase equilibrium and the microstructure evolutions also. So, that is the so therefore, you need to connect data science with this whole picture, what is known as ICME, integrated computational materials engineering, which is the big umbrella that requires a lot of data. That is the basic goal. Data will be connected with the ICME approach to calculate phase diagrams and understand the phase informations. And now, in case of CalFIRD, we have to use 5 different things. First, we have to capture data either from experiments or the calculations, analyze and monitor the or modeling the data, which is called assessment part as shown here, and then followed by optimizations, because we need to fit certain parameters to optimize the thermodynamical functions. Finally, we store the data, some data files, which can further be validated using experimental data. Finally, it will be applied for various kinds of uses. So, there are 5 steps: data capture, assessment, optimizations, storage and validations, and this requires, that is what this finally generates thermodynamic database, which will be widely used for various kind of applications. One can look at this thermocal website for details of these. So, that is what is shown here in this sense, and Gibbs free energy is calculated Gibbs free energy is basically found out for all phases using this approach, which is called assessment and optimizations. So, one can do thermodynamic calculations, one can do diffusion calculations, which is called diffusion interface control phase transformations, as well as one can do also both together, which is done is Prisma. So, I do not want to go in details of this. This is the thermodynamic approach I used, I talked about it. So, thermodynamics means free energy, we talk about gives free energy in material systems, that has three components, which is called the pure components, the entropic or mixing component, and third is the excess entropic contributions. That has to be assessed properly, because that is the difference between the actual free energy and the free energy obtained using both the pure component and the entropic contributions. Okay. So, you can see G excess is nothing but G minus these two terms, right. So, therefore, G excess has to be measured or obtained from binary data sets. Once you have, this is possible to obtain, because we know the binary phase diagrams of all the systems are available in the literature. So, you can easily get that, but ternary and quaternary may not be available, higher order systems may not be also available. So, what you do is extrapolate the free energy from binary to ternary and quaternary. Finally, this free energy functions are obtained and they are globally minimized to get which phase is stabilized more or less. So, we also discussed about something about phase field simulations, and in particular I talked about how to obtain microstructures in a precipitation formation systems like aluminum copper alloy. And main idea of this phase field simulation is to solve a single set of partial differential equation of the entire domain. So, remember there are two aspects in phase field simulations, because we are talking about a phase transformation, right, from a single phase microstructure to a precipitate plus matrix. So, we need to have information of thermodynamic information like bulk thermodynamics, as well as we need to have information about the surface properties, interfacial properties, and diffusibilities also. So, these two together must form a single set of partial differential equation, and this, that is why phase field model incorporates both the bulk thermodynamics of the multiphase systems as well as surface thermodynamics like gives surface excess quantity, which is nothing but surface energies. And free energy is always approximated like that, is the total free energy is a volume free energy plus surface energy. And we know that important aspect in phase field simulation is to assume the evolution of the one variable phi as a function of time. So, therefore, for the whole system, when you are talking about phase transformations, phi is allowed to vary continuously from one phase to other phase via the interface, as is what is shown here. For this phase at the top, the phase phi value is 1, for this phase phi value goes to 0. In the interface, phi value varies from 1 to 0. So, that is why actually we can track the interface very easily by simply looking at the values of the phi as a function of time, how it evolves. So, for solid liquid phase transformations we can use this kind of phi is 1 for solid, liquid is 0, and so that is this is the in the free energy expression. You can see here this term is basically coming from surfaces or interfaces, and that term next term is coming from bulk free energy, the bulk. So, we obtain the free energy, then we can solve this dynamics, a variation of phi as a function of t using this equation, where m is called mobility, and this mobility is nothing but related to diffusivity. So, that is one can easily solve, and we can actually have different kind of free energy equation. Now, basically we need to use double well potential to do that, like this kind of functions or this kind of functions to be used. Here you see that for phi is equal to 0, g is 0, and phi is equal to plus minus 1, g is equal to 0. Here for phi equal to 0 it is 0, and phi equal to 3 by 2 it is also 0. So, therefore, we have a double well functions, as you can see here. Here also you have a double well function. So, it will come down and become 0 sum. So, that is why this kind of functions actually help us to make the simulation better, and for liquid solid we always use free energy differences between the solid and liquid, and that is nothing but latent heat multiplied by under cooling divided by the melting temperature, and do that. So, I do not want to go in details of each of these functions and all this stuff, which you can read from my earlier lecture as well as from the Stokes. So, we can make various kinds of simulations here. We can have dendritic growths, as you can see here. Nice dendrites are growing. These are taken from NIST, National Institute of Science and Technology, USA. We acknowledge their availability of this kind of microstructures on the websites. So, therefore, the microstructure evolutions of solid to liquid phase transformation can easily obtain. We can also show how these microstructures dendrites can form in a liquid to solid taken from GMAC, Mullis and Losum of University of Leeds. So, that was something I discussed. Now, next of the lectures were discussed by Professor Tarun Kumar Kundu, that is on lecture number 32 and 33, and here briefly I will talk about it what probably has been discussed. With important aspects in for electronic and atomic structure is what is known as the Schrodinger equation. Okay, that is nothing but H psi equal to E psi. H is Hamiltonian and E is the energy. Okay, and this is something which is the one which shall be widely used. So, electrons are presented as in molecules as well as materials or atoms. We have to expand this psi, which is the wave functions that provides you atomic orbital or plane waves, solve this equation for self consistency, and we can obtain property like energies, molecular orbitals, densities, and we can also obtain spectroscopic properties like NMR, IR, UV visible things also, because they are also electronic interactions. So, once you can understand electron structures very easily by or solve this, then it is possible. But this equation is not a standard equations, it requires a lot of understanding. Solution of this equation for multi atom systems or even multi electron systems is very difficult. It is easy to solve for hydrogen and helium probably, but for multi electron system it is not easy to solve. So, consider a single hydrogen atom, it is possible to calculate the potential energy very easily, and we can also calculate the kinetic energy. So, total energy is equal to this. So, now H psi equal to E psi can easily be solved, and we can find out from the psi the electron distribution. So, probability of electron will be dependent on an absolute value of psi square, So, we can easily find out that. So, one can also find out elastic properties by looking at these kind of binding energies. This is the bell curve, this is summation of total potential energy plus kinetic energy. Simply we can find out this, and then we can also find out the minimum distance between the two atoms. Well, so hopefully this bell curve, I am not discussing much of that. So, this is something which is very easy to do, but this allows us to prevent the localization of electron near the proton, and that is the uncertainty principles. And it also retards the collapse of the atoms, provides correct density of the matter, and also yield the proper binding energies of the atoms also. This particular theory is very important. But when you talk about electrons are not only particles, they are also can behave like waves. We all know de Broglie's equation, right. So, we can convert the momentum in terms of the wavelengths very easily. Wavelengths of a particle depends on its momentum, just like a photon. The main difference is that the matter particles have mass and photons do not have mass, that is the main difference. Well, that is about the electronic calculations using the Schrodinger equations. One can do actually consider atoms also, atomistic calculations also, consider atoms as a particles moving in the matter. Okay, then you can solve the Newton's equation of motion. That is what is shown here. You can see here acceleration is shown as a force divided by the mass. So, we know that force is nothing but mass into acceleration. So, we can write down mass and acceleration is like this. So, therefore, we can calculate, we can write down acceleration like this is nothing but force by mass, easily we can do the calculations. And this can be integrated and we can find out the location of each atom in the whole system. So, we can do movements of atoms, solve numerically and propagate. That is how we can find out reaction rates, diffusion coefficients, stress strain using MD simulations. MD stands for molecular dynamics. Okay, this is what is called MD. It solves the Newton's equation of motion. Furthermore, we can also do electronic structure calculation using ab initio. That is what is called a density functional theory, and this is something which is widely used. DFT based time binding models allows us to find out nearest neighbors, minimum basis. We can also use semi empirical models like MOPAC. We can feed the experimental data, find the nearest neighbors, minimal basis also. Finally, what you are doing to try to do is that by that you are going to find out the electronic structures in the material. So, how it is done? Simply solving set of equations, which I will not go in details of that. I hope you have learned from Professor Kundu's lectures, but it allows to find a density function of or density, electron densities in terms of energies, that is what is shown here, usually is expanded in orbitals, and then one can apply various kinds of boundary conditions to solve that. But please check more literature to understand this. This is something which you have to do yourselves. So, this is in a nutshell what we discussed about the last 4 lectures of different kinds of computational techniques which will be used to calculate or generate data. Let me also tell you that the cost and the number of atoms. So, classical force field you can use almost like 100,000 atoms, cost is very low, it scales very easily with number of atoms. But semi-empirical methods or reactive force field methods, semi-empirical method especially cannot use large number of atoms, right. But you know MD can use very large number of atoms, 100,000 atoms or so, that is what is classical force field methods. Okay. Now, DFT can use very small number of atoms, 500 maximum, and it scales with 10 to the power 3 minus 1, it is very costly, relative cost is almost 10 to the power 4 or 5 times larger. Typical accuracy is very large, can see that compared to this and this. And finally, one can actually go to better methods like CCSGs, and there you can actually use only 30 atoms, okay, to do the DFT calculation. That is what nowadays done, and relative cost is massive, and scaling is 10 to the power 9 is 10 to the power 7, and we can get down to typical accuracy of 1 kilocalorie per mole. So, it tells you how accurately you want your data. If you want more accuracy, you have to pay more cost, or you have to use better systems, time also will be larger. So, that is why this depends on the system and properties what you want, I just wanted to provide. So, with this let us move into the advanced deep learning techniques, okay. And this is something which requires a lot of data, and that is why actually this scaling materials systems, all kinds of scaling things we talked about it, starting from basic things like CalFAD to about DFT can generate a lot of data, and these data then can be used for deep learning or advanced deep learning techniques, that is something. But here we are not going to discuss everything, because that will be quite a lot, and that time also is not there to discuss all the advanced deep learning techniques possible. We will focus about 3 techniques. There is a DTL, DRL, and we use DTL, deep transfer learning. This DTL comes from DTL, DRL, that is a deep reinforced learning, enforcement learning rather, and third one is NLP, natural language processing. Okay. These 3 things we will focus on that, but for this lecture number 34, we are going to talk about DTL and DRL. Well, first to give you some aspect which I already discussed, deep learning is very important, and it mimics the neural network systems in our brain. That is why it can allow the computers to understand recovery patterns. It can allow us to make decisions from vast amount of unstructured data. Remember this, vast amount of unstructured data. That is why it is used in various domains like the computer visions, NLP, healthcare dynamics, autonomous driving, and NLP and computer visions are very important for material science, because we are going to deal with a lot of images, we are going to deal with a lot of literature, how to use deep learning in this kind of situation. So, it is basically typically based on neural network architecture, and we already talked about a lot of these things in ANN, artificial neural network, with part of ML methods, and also a part of deep learning methods in some lectures, earlier lectures. Okay. So, and we know that why use deep learning, because it provides you much better accuracy, performance is better, especially it provides excellent solutions for uncovering complex architecture in high dimensional data. It provides a key role in building intelligent data driven systems, whatever you need today. It can also change the world as well as humans' everyday life through autonomous power and learning from experience. So, DL is capable of learning from data and generate the patterns autonomously. That there is a strong linkage between DL and the data science, which we will discuss even at the last part of this course also. And deep learning is good when your data are amount of data are large. ML is very good or rather good when your amount of data are less. So, what I can conclude is that deep learning performs much better than the ML when for big data. And we talked about ANN, we talked about CNN, we talked about RNN, we talked about autoencoders, and we talked about also deep Philip network or DVN also. These are part of the normal deep learning models. This chart shows you what all deep learning methods possible. Remember supervised and unsupervised learning. In supervised we talked about MLP, okay, that is the multi-layer perceptron model. We talked about CNN, okay, we talked about RNN, and then as a part of RNN we talked about LSTM also, GRU also, right. I hope you remember. And unsupervised learning we discuss mostly autoencoders, AE, general adversarial network, GAN, SOM, we discussed about it, right. So, therefore, the advanced deep learning techniques will combine two different techniques together, like model 1 will provides you combination of CNN versus LSTM. LSTM is a part of RNN, okay, recurrent neural network. So, therefore, and the model 2 is talked about GNN plus CNN, and that is called net versus plus the generalized adversarial network, we discussed about it. Model 3 connects one of these generative supervised or unsupervised learning with classifiers like SVM here, correct. We can also use that is what we talk about it, we can use DTL and DRL, that is what we are going to talk about today, what is DTL and what is DRL. So, first let us talk about why you need advanced DL methods. As you know, supervised models are unable to learn from unlabeled data, but it outperforms the unsupervised generative counterparts. That is what is very important to understand. These models cannot learn from unlabeled data, because they are supervised models, but they can actually give better performance some cases in compared to unsupervised learning. On the other hand, unsupervised learnings are more adaptable. They have capacity to learn from both labeled as well as unlabeled data. Basically, they are more useful with unlabeled data. I hope you know now what is labeled and unlabeled data. So, hence if we can make a framework for training both these supervised and unsupervised model simultaneously, we can enjoy the benefits of both the models. That is what is the motivation of using advanced DL, and this means we have to use hybrid networks, so hybrid DL models. That is what I talked about it, hybrid, you can see hybrid learning methods here. That is what we need to discuss in this lecture. And what is this hybrid DL? They are typically composed of multiple deep basic learning models. Okay, we have just discussed about basic models, right, already a lot of basic models you have learned. So, these hybrid models will basically composed of multiple deep learning models, where basic model is either a supervised model or unsupervised model. That is why we need to integrate different models, and that is very important, and this is something which you will see how more. So, how can you hybridize or how can you make hybrid DLs? Like you can have a model type 1 in which you can integrate different generative or discriminative like supervised or unsupervised models. Remember, generative means unsupervised and discriminative means supervised learning methods. So, therefore, we can combine these different supervised generative models to extract more meaningful and robust features like CNN, ConvoNet plus LSTM, okay, or AE plus GNN. Okay. We can also use hybrid model 2 which is nothing but the integration of supervised model followed by unsupervised model. Example is DBN plus MLP, AE plus CNN. We can also integrate a generative or discriminative model by followed by non deep learning classifier like SVM, AE plus SVM or CNN plus SVM. So, we can do this kind of hybrid modeling to obtain a better of two models. Okay. So, let me stop here for this part of the lecture. We will come back to the next part of the lecture where we will discuss more details about these DTL and DRL methods.